Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is lecture series on analog signal processing, and we are doing different aspects of the analog signal processors. In the whole syllabus, we have discussed different points for the analog signal processing. We have started with the introduction, then the basic building blocks, the blocks which are used for the filter design, the biquads, quads. Then we have designed some of the standard filters which are like Butterworth, Chebyshev. After that one, we have designed some of the active components that can be used for the analog signal processing. Now we are reaching toward the end of this syllabus, and now we are discussing the transconductance, which can be the ultimate replacement of all the building blocks of the analog filters. We can replace the elements of the analog filters like R, L, C components using transconductance, which is known as GMC. In the last lecture, we have discussed the elementary transconductance building blocks. Here again, we are discussing the other building blocks. In the last lecture, we have discussed the resistance and the integrator. Now, we have designed transconductance in single-ended transconductance and the differential transconductance. In the last lecture, we have also seen that how a transconductance from the single-ended to can be converted using the differential transconductance. The ways or the points through which we can change single-ended transconductance circuit to the differential one. So we have discussed how single-ended circuits can be converted into the differential order. First of all, we have to design a single-ended circuit. Then we can take its mirror image of the single-ended circuit with the reference of the ground, and then we have to take the polarities of the single-ended and we have to change it for the mirror image. We will change the polarity of all the inputs as well as the output of the active devices. Here active devices are transconductance. Then we have to take double the values of grounded capacitor. We have seen that we have to double the capacitor value because of the change in the voltages and the currents, both are doubled. And we have to leave unchanged any value of the capacitor that is connected differentially. And lastly, we have to discard any input which is grounded. Any input which is grounded, that may be discarded. And we have to merge all the active devices with each other to make a fully differential device. So lastly, we have to merge all the corresponding active devices. This will make a single-ended to the differential mode circuit. Now, after this one, after having an integrator discussion and the resistor discussion, we can convert an amplifier into the our transconductance. Now, transconductance is a OTA, operational transconductance amplifier. So it's already an amplifier. So voltage amplifier using transconductance amplifier can also be created. We know that if we have a load transconductance GM, if we load this transconductance GM with a resistor 1 by GM2, then then if we take the output of this one, the output of this circuit, that we have a resistance which is loaded with a transconductance GM1. So this is a transconductance circuit which has a load of resistance, let's suppose R, and R is equal to 1 by GM2. We have seen this relationship and this circuit in the previous lecture. So this circuit, if we go for this circuit, the output of this circuit will be V2 is equal to GM into GM V1 into R. We know that this is equal to IO for the 1. So we can have simple relation V is equal to IR. And if we put the value of I, it is GM1 into V1. So from here, if we put the value of R also, R is 1 by GM2. So I have replaced R by GM, 1 by GM2. And now what will be the transfer function of this this whole circuit? It will be V out V2 by V1. V2 by V1. So if we say V2 by V1, this is a transfer function or gain of this this whole circuit. It will be GM1 by GM2. Or we can say that this is a single-ended amplifier with the gain of GM1 and GM2. GM1 by GM2. Now, if we want to make its differential form, differential amplifier, this is a single-ended amplifier. This is single-ended amplifier. Now, to make it differential amplifier, we have to take mirror image of the this whole circuit. So, if I take a mirror image from the ground, then we have to connect the mirror image, and then I have to discard the grounds and then merge the active devices. So this whole makes this circuit where I have this, and I have to take the inversion of the devices. So if I create a mirror image of this one, this will be, one is grounded and other is V1. This will be negative, this will be plus. This will be negative. After making the mirror image, we have to invert the polarities of the active devices. Then I will have, this will be given to the negative, positive will be grounded. So it is given to the negative, and positive will be here, and there will be a feedback to make it a resistance, load resistance R. So now if we, these are the mirror images, if we merge these two, the negative will be go to the negative, so negative is given to the negative, and positive will go to the positive, will go to the positive, and the outputs are from the positive and the negative. So differential output will be one positive and the negative. Also the inputs are V1 and V1 dash. So two inputs are there. So this is the single-ended, and we can merge grounds to make of the mirror image with the negative, with the opposite polarity, to make a fully differential circuit. So this is an amplifier with a fully differential circuit. Now, another important elementary building block is summer. Summer is a circuit which gives sum of all the currents or all the voltages that are applied. So if I have different inputs V1, V2, V3, then we can have output which is equal to the V1 plus V2 plus V3 and so on. Or if we have currents I1 plus I2 plus I3, then all the currents I1 plus I2, I3 will be the output. So summer is simple to be created in this transconductance amplifier, because the output of any transconductance amplifier is current, and when we have a current, because it is voltage controlled current source, so if we have a current, that is output, by using simple node, the currents will be added up. For example, if we have these four transconductances amplifiers, GM1, GM2, GM3, GM4, four different voltages are applied, V1, V2, V3, V4. The outputs will be I1, I2, I3 and I4. Then all the currents will be added up at this node, to give sum of all the currents, I1 plus I2 plus I3 plus I4. A resistance can be used. Again, resistance can be created using transconductance amplifier. So I have used a transconductance amplifier resistance to convert this current into voltage. So the output is again voltage, which is a sum of all the voltages. Another important aspect is that if I want to subtract some current, I have to take with the single-ended amplifier, single-ended transconductance amplifier with the negative output, inverting output. So we can say that to add the voltages, first of all we have converted the voltages into currents using transconductance. Then all the currents are added at a node. By simple Kirchhoff's law, we can add up all these voltages. Then at the end, we have to convert the current to the voltage by using resistance. So this will be V1 plus V2 minus V3 plus V4. So we have amplifier, resistors, integrators and summers. Now another important element is gyrator. We know that gyrator is important when we are going to simulate inductors. To simulate inductor, we need gyrators, and in the previous unit we have seen that gyrator is a circuit whose input impedance is proportional to the load impedance, or we can say that its Zin is proportional to 1 by Z load, and proportionality constant was R square for the GIC. Here the proportionality constant is Gn, which is transconductance. So we can replace this by proportionality constant by Gm. So we have seen that whenever gyrator is loaded with the capacitor, that GIC when loaded with a capacitor, that act as inductor. So let's take this circuit for to make it a gyrator. Let's suppose we have two circuits. Let's suppose we have two transconductances set up in this arrangement such that the input current is given by to the second of the second GIC, so second transconductance input. Then we can say that I1, which is GM2, and the input voltage is, let's suppose, V2, which is over here. So if the input voltage input voltage to GM2 is V2, then I can say that I1 is equal to GM2 into V2. Similarly, for this circuit, I will have G1 into V1 is equal to I2, which is the transconductance equation. Now, from these two equations, if you take the ratio of these two equations, I have I1 by V1 is equal to 1 upon GM1 GM2 into V2 I2 by I1. Now if I say this one is 1 by Z load or Z2, and this is Z1, which is input resistance. So this whole circuitry, the input load is proportional to the output load. So we can say that this circuit can act as a gyrator. Okay. So I can say Z1 is equal to 1 by GM1 GM2, which is the transconductances of the two transconductance amplifiers, and then into V1 Y1. Now again, if we take the load, or if we take Y2, the output load is capacitor, then it will be again 1 by SC. 1 by SC means, so it can be taken as SC by GM1 GM2. So if Y2 is capacitor, Y2 will act as a inductor. The whole circuit will act as the inductor with inductance of L is equal to C GM1 GM2. So this whole circuitry act as inductor idle. If we have transconductance as idle, we will have an idle inductor. This will act as an idle inductor if we have idle capacitor as well as the transconductance amplifiers are idle. However, this is not the case. There is some parasitic capacitances which always hindrance with the capacitor C. As we have seen in the previous cases also, there is some model which gives the internal capacitor C0 Cin. So if we include from the model, if we include the internal capacitances of the MOS also, then we have designed this model. We have designed this model in the previous case, A model. So if this model with the passive resistance and the capacitors, resistances and the capacitors, if we apply a capacitor C, then we have seen that the input capacitances and the output capacitances for the differential mode, it will be, the total capacitance will be C in parallel with R, in parallel with C0 and in parallel with C1. So all these capacitances will be added up. So if we take the transfer function in the whole, the resistance as a whole, it gives Y1 plus G0 plus Ci plus C0 S plus GM1 GM2 upon SC total capacitance plus G0. We have driven this equation in the previous lectures also. So this gives the change in the whole capacitance by C. So all the capacitor values, the capacitor value has been shifted by C plus C some value. Plus there is a resistance G which is included in the this circuit also. So this whole circuitry gives different value of capacitor and the inductor when we have a parasitic capacitor or the internal capacitance taken into consideration. Another aspect is the floating inductor. We have seen that floating inductor is mainly used for the ladder circuit. So when we have a floating inductor, we have to use same as in GIC, we have to use the two different gyrator which are implemented back to back. So if we go with this one, we will have a gyrator which is similar to a floating inductor. And the equation for this one can be taken as I1 is equal to I2, because input currents are given for the from the output, the output, the whole value will be same. So I1 is equal to I2 is equal to GM square SC into V1 minus V2. So if this is 1 by S, we will have an inductor. An inductor which is not grounded. It is the difference of V1 and the V2. So both are inductors which is floating. So in this way we can from transconductance GM we can create different elementary building blocks. For example, we have created resistance from GM. We have created integrator. We have created summer. We have created summer. We have created amplifier. We have created gyrators. Which is ultimately inductors. So these all things are required to create different filters. So we can create all these things using GMC circuits. So any circuit that is to be designed that can be used using GMC. Thank you.